Okay, let's continue on the transmission lines. On Wednesday, we finished the resistance of transmission line. Then we moved to the inductance of a transmission line, and we utilize the definition of the inductance of transmission line, and we find the flux and flux linkages. That is related to the current of the conductor is carrying. The approach we took, we first investigate the flux linkage inside of the conductor, and we find a formula which just indicate how the inductance is calculated based on the flux linkage inside of the conductor. And we also have the inductance depending on the flux linkage outside of the conductor. And the first one, the inductance inside due to the flux linkage inside the conductor doesn't depend on the dimension of the conductor, so which is a constant value. But for the inductance, depend on the outside of the linkage, depend on the linkage flux linkage outside conductor does depend on the distance to the conductor. Okay, so if we combine the two parts, if we consider just a single transmission line with one conductor sending current into coming out from the screen and going back to the screen. So for this case, to calculate the inductance for each conductor, we consider the internal inductance, and for the external inductance, we need to define two distances. The first distance will start from the skin of the first conductor, so that's a D1. And for D2, we're going to use the distance between the two conductors, so that's D2. Okay, so we combine the both, we prove, finally, we get this a single formula. So this formula is good to calculate the total inductance for each conductor if we know the dimension of the conductor. So here the ds is called the GMR, geometric mean radius of a single conductor. And the d is distance between the two conductors. Then let's move to more complex cases. For example, we still have let's just think about the single phase AC circuit. We have one transmission line sending current I, maybe just coming out from the screen, and we also have another line sending the current back to the screen. So the current will be negative I. But we make one line to have three conductors as a bundle. And the other line will have two conductors as a bundle. Okay, and so each bundle they're connected directly. So and can be treated as just a single phase line. So how do we calculate inductance for this case? We still start from this formula, but this formula is only good for the case like we have just two conductor, which means if we treat the first line has n conductor, second has m conductor, and this is special case for m equals n equals 1. Okay, but now we have we need to be able to treat any number of conductors on each line. So which means we need to extend this d to be some more general d, which is geometric mean distance. Geometric mean distance is just like average distance between the two group of conductors. So assume each group you have a fictitious center of that group. So if you measure those two centers, that will give you a GMD. So this is basically just it just generalized of the distance between two conductors. So how about the radius for each group? Similarly, if we treat each group as a fictitious single conductor, so that radius will be the will be the radius we can utilize in this formula. Okay, so this one is called the GMR. GMR stands for the geometric mean radius. Definitely the two groups have different shape, different number of conductor, so their radius can be different, which means if you calculate inductance for each line, and the two values can be different. They don't have to agree with each other. So how do we calculate the GMD or GMR? So assume we have a shape which is not perfectly symmetric. They have, like in this case, we draw just three-dimensional volume, and we can always get a cube of the same volume. So to calculate the volume of this cube, we just calculate multiplication of all the dimensions, the length of all dimensions, then we calculate the geometric mean. So this one will give you the equivalent dimension of each, the length of each dimension. So which is like an average of the length in each dimension. So we can use the same idea to calculate GMD and GMR. Okay, so here we can ignore the geometric asymmetry of each bundle if we utilize that idea, geometric mean, to calculate the average. Then we're going to use the average to replace the distance and the radius. Then we'll be able to use the same formula. Okay, so assume that the final generalized formula is this one. So we already replaced the D to GMD and R to GMR for each bundle. We call it the GMR S and GMR Y because two bundles have a different number of conductor or different shape. So we're not sure they have the same average or mean radius. So how do we calculate the GMD or GMR? Okay, first GMD. GMD is just defined as the average of all possible distances between the two bundles. So what does that mean? Like for this case, for the first bundle, we have three conductors. Second, we have two conductors. So if you draw a line, straight line connecting one conductor from group one, the first group, group X, then connect to a conductor belonging to the second group. So this is single line. Okay. You can also draw another line. You connect A to E. So there's another line. So that's second distance. And you can do the same thing for B, E, then C, E. So how many distances do we need to consider? So it's 6, right? So the first group is from A to anyone in the second group, and the second group is from B to anyone from the second group. Then the last one is the from C to anyone in the second group. So you have 6 different distances. You want to calculate the average. So you get the root of the product of all distances. So this will be the defined as GMD. Okay. Similarly, we can use the same formula to calculate GMR. GMR will be the average of all distances belonging to just one group. Okay. Not considering the other group. Like for instance, if we want to calculate GMRX, how many distance can we generate among the group one, between the group one? So we have like AB, right? BC, AC, but definitely those are 3 distances between the 3 conductors, but we also need to consider the distance between one conductor and the cell. So which means we need to first define reference, and for each reference we count all the differences, and by changing the reference we need to cover all possibilities. So what we're going to do is let's select A as a reference. So this is center. So we need to consider the radius of the conductor A because because the radius means if there's a center, any point inside of this group to the distance to the center, and we count all possibility to calculate average, that will be the geometric mean radius. So we count the radius of A, and we count the distance to B, and we count distance to C. So there are 3 distances we need to consider for just conductor A. Then we change to conductor B and conductor C. So finally, we have 9 distances in first group. Okay, which is this one. So we have for each conductor, we need to consider 3 distances. So when we calculate the product of 9 elements and calculate their root, that will be the GMR. So here for the radius for each component, we just call it the DAA, means just the radius of it just means the radius of the first conductor. So here we just take the ds. ds is actually it's not the actual physical radius. It's called the GMR for a single conductor. So there are 9 elements. So next, if we want to calculate the GMR Y for the second group, how many elements we need to consider in the product? Any idea? So for the group X, we have 3 conductors, and using each conductor as reference, we consider 3 distances. So 3 by 3 is 9. And for the group 2, we have 2 conductors. So using each one as a reference, we have we draw 2 distances. And by changing the reference, we get another one. So it's a 2 by 2. So we have 4 elements. Okay. So you see, by using this example, we can explain when you calculate the GMR for each group, you just use each one as a reference, right? You consider the radius on its own and the distance to any one in the same group. Then you change the reference to another one. Okay. So finally, if I have 3 elements, so that will be a 3 by 3. A 4 element will be 4 by 4. So that's GMR. GMD is just any distances connecting the 2 elements from 2 different groups. So the total number will be 3 by 2, 3 multiplied by 2 by this case. If I have n conductor in the first one, m conductor in the second, the total number will be n times m. The total number will be equal to the product of n and m. Okay, next. So in reality, if you look at the 3-phase transmission lines on the high voltage tower, usually the line is not laid out at like a perfect triangle of 60 degrees, right? So usually one distance can be longer and one distance can be smaller. So how do we deal with such a asymmetry? So there's one idea is called transposition. Transposition means if the distances between A and B, A and C, and B and C are not equal, but that is due to the limitation of the tower, the shape of tower. But you can change the sequence of the 3 lines when you move to the next tower. So eventually you get average the distance to be same. Okay. For example, this is the first tower. When you move to a second tower, you use the position B to carry the original line A, right? Then you move B to C, then you move C to A. So which is like you keep changing the order of the line, but you keep the same shape of tower. One picture will be like this one. So if you have interest to look at the high voltage tower, sometimes you can see some tower has more complex layout of line because they are doing the transposition. So for example, if you can see, let's just assume this is A, this is B, and this is C. So you see the A will connect when we reach this tower. So they will connect it to a point at B. There's a wire connecting from A going down. And similarly, B, you can also see there's some wire going down. Then the C will be some wire going up, right? So it's like, so that will make this one be A, this one be B, and this one be C. Okay, after a certain distance, they will do such thing, and they will change the sequence over long enough distance. Eventually, we can just roughly trade. The distance between any 2 phases will be same. So that will be the GMD. So JMD for this case, so if you calculate the inductance for each phase, and the final inductance for each line will be the average of the three inductances. So which is equivalent to just calculate the JMD here for this case. All right, so that will be the formula to calculate the L. So we replace the distance between two conductors to the JMD for three conductors, three phases of the line. Yeah, definitely. If your tower is able to have the equal distances between all the three phases, that go back to the original formula. So that's it. That's everything we need to know about the inductance. And next, we move to a capacitance of the line. So it basically take the same approach, but as I explained, so for capacitance, it's defined as the charge divided by the voltage, right? But there's one difference, key difference between the electric field and the magnetic field. The magnetic field can exist inside of conductor, even magnetic material, but electric field cannot stay inside of the conductor. So that make the derivation of the capacitance for transmission line simpler than the inductance for transmission line, because we don't need to consider the flux density inside of conductor. We only just study outside. So remembering we have very complex slides, right? Going through the method by calculating flux linkage outside of a conductor, inside of a conductor, and then we combine the inductance together to get the final formula. But for this case, we only need to do the outside. We don't need to consider the inside for the electric field. So that make it easier. Okay, so we start from the definition of a capacitance, and then we define the electric flux density. Electric flux density, usually we call it D. D just defined to be the charge. Assume there's inside there's a positive charge. The positive charge will have flux going away, right, to the infinity. If there's no another negative charge, it will go to the infinity. But if there's a negative charge, that flux can be changed, right? Eventually will go to the negative charge. Yeah, that's an electric field. So which means you can count how many fluxes here divided by the area you circulate, you cover that charge, and that will give you the density of the flux. But this is an electric flux, not magnetic flux. But this formula is equivalent, it's analogy to the formula for magnetic field. Okay, so we know for the magnetic field, the B means really the density of flux, and H only depend on the strength of the magnetic field. But their difference is only just a ratio, mu zero. Similarly, for the electric field, we can define electric field intensity, which is the strength of the electric field, and it's equal to the D divided by this coefficient, this ratio. Here we call it epsilon zero. Epsilon zero is similar to mu zero for magnetic field. Then you plug in the first equation, you will get the formula to calculate the electric field. So mu zero here is calculated based on the speed of light in outer space, and also the mu zero. Okay, epsilon zero is called permittivity of free space. So the mu zero is defined value. So epsilon will be a calculated value. So this one is not like the number like mu zero, which is very easy to memorize. But you can, it can always be calculated using this formula. So do you remember what mu zero is? Mu zero is 4 pi times 10 to the negative 7 Henry per meter. So that's defined value. So you can use mu0 C to calculate the epsilon 0. Okay, so next we're ready to calculate the capacitance. The capacitance, first we need to calculate the voltage. Think about there's two shells surrounding this conductor. So one shell has both shells have the cylinders. The first one has the radius of d1. The second has radius of d2. If you can move charge from d1 to d2, if the center is a positive charge, if you move from d1 to d2, the potential will decrease. So you will generate a positive voltage. Okay, so that positive voltage, and we use the charge divide the positive voltage, that will give you the capacitance. So once you define the D1, D2, and the Q, you'll be able to calculate the capacitance. So here we just first need to calculate the voltage. Voltage is defined to be just a potential change if you move, which is defined as the work done moving a unit charge from the distance D1 to distance D2. So basically just integrate the electric field for the change of the distance from D1 to D2. So you just plug in this formula here and you solve this integral. You will get this one. Okay, so this one tells the voltage drop from D1 to D2. And okay, then we're ready to use this one to continue to study the capacitance. For capacitance, we have to assume a certain layout of the transmission line. The similar transmission line will have two conductors. So one conductor may be sending the current, the other is sending current back. So, right, so you can think about here, there's a load, but on the other side, there could be a source. But that is similar circuit you can think of, which is single phase AC circuit. Then if we treat the entire circuit has net zero charge, which means it doesn't make sense for the circuit to carry positive charge or negative charge. So which means if one conductor is at this moment is carrying positive charge, the other will be a negative charge. So their charge will be opposite to each other and at same radius and the distance of d. So let's calculate the capacitance for those two conductors. So conductor 1 carries a charge Q. This charge is just a unit we consider for each meter, coulomb for each meter, C per meter. So that we basically this formula for D2 will be the distance, and D1 will be the radius. Okay, so this is the voltage due to the first conductor. So if your first conductor has this positive charge, right, the flux will leaving from the conductor. The second one has to carry the negative charge. The flux will come back. So this voltage only calculated based on the first conductor. So your second conductor, you have a negative charge that actually create another electric field. Also generate some potential difference between the two distances. So we also need to consider that one. So we need to consider conductor 2 carry a negative charge. So basically that same formula, we just swap between 1 and 2, and we replace Q by negative Q, right? That's just application of the exactly same formula. Okay, so the two voltages will add to each other. So the final voltage will be the one we are looking for this formula to calculate capacitance. So we need to swap the subscripts because we want to add the second to the first one. So we change from a 2-1 to 1-2, and which means we change the charge from a negative Q to Q. So next we just add those two together. Okay. So you see those two actually identical. Basically, we just get rid of the 2 on the denominator. So this will be the the total voltage due to the positive charge and negative charge on the two conductors. Okay. Then what is the capacitance? Capacitance for this case, because we use the voltage between two conductors, the capacitance we're going to calculate will be the line-to-line capacitance. So it's defined to be the charge Q divided by total voltage. So basically, just we just plug in this formula to the V12, and Q is canceled. So we'll have the capacitance. Does it make sense? Okay. Yeah. Let's move on. So okay. So now what we have if we have a two conductor, they together make a single circuit. And what we proved is a formula to calculate the capacitance between the two conductors, which can be calculated based on this one. If we know the radius, we know the distance, we'll be able to calculate the total capacitance between the two conductors. But this is not convenient to use because if we are operating a three-phase transmission line, the three-phase transmission line has three conductors. So which one should we calculate? We need to calculate the capacitance between A and B, B and C, A and C. More convenient idea is we just calculate capacitance for each conductor. Okay, we can create another reference. The reference can be ground or maybe neutral point. We just calculate capacitance for each line, each phase relative to the neutral point. So if needed, we really want to calculate capacitance between two lines, we just add the two together. Okay, so this equation is good, but it's not convenient to use. So we can assume there's some neutral point. The neutral point is just at the middle of the connection between the two conductors. So if one conductor is carries charge Q, the other is negative Q. We know, so this point will be equivalent to the ground because it will have zero potential, right? Because positive charge and negative charge, if they're symmetric in this layout, the middle point will be the ground. So neutral point is like ground. So we just split the capacitance into two capacitance. We call it a C. They just connected in a series connection. And each C means the capacitance to the ground or to the neutral point. Okay. If the system has a zero net charge, the neutral point is exactly just ground. So C is what we can use for calculation for each line. So what is C? So if the total capacitance between A and 1 and 2 is C12, and we split that into half, what is each C? Okay, it sounds like a C can be a half of the C12, right? But actually, if you split, if I have a single capacitance treated as series connection of two capacitance, so each capacitance has to be double of original total capacitance. So that's different from resistance or inductance. So we define capacitance per conductor as C. So this is what we want to find for our calculation. So C is defined to be, it's still the same charge, but divided by half of the voltage because we only just use the voltage between one conductor to the neutral point. So you see there's a factor of 2. So this one will move up. So C is actually equals to double C12. Then we just double C12 means you add factor. So this is actually the C. This is what we're looking for. So we're done. We have find the formula to calculate capacitance for each conductor. For each conductor, we can use this formula. So because in reality, usually we'll consider transmission line longer than maybe a kilometer. So this unit is more convenient. So if you use this unit, this number will become 0.0556. So we can use this formula. Okay, so based on our experience, finding the inductance for bundled conductor, we know we only just need to change the D to JMD. and R to JMR, right? So we can easily just take the same form of the formula and just get this general formula. So this formula is good for any cases. No matter how many conductors you have in each bundle, in each group. When you calculate capacitance, you only need to calculate two things. The first one is the GMD, the geometric mean distance, second GMR. But here, we hesitated to use the same GMR for inductance. We just call it GMRC. Because as I explained, electric field doesn't stay inside of a conductor. So when you calculate the radius, you want to exclude the inside flux, the flux inside the conductor. So this GMR will be different. You can also, actually, you already noted that. So here we use R for this case. The R is different from, it's not the DS. For inductance, we use DS. Right, DS is smaller than R, slightly smaller than R. It's about 0.78 times R. Okay, so which means this GMR is also will be slightly bigger than GMRL for inductance. So we can compare that formula to this one. So it only just depends on the GMD and GMR. But GMR here, we put L, so that's based on the, that doesn't use the actual, the radius of the line. All right, so from the two formula, we can conclude such observation. So if the GMR increase, it doesn't matter it's GMR L or GMR C, but finally just the average radius among the conductor of same group increase. If GMR increase, so this GMR increase, this GMR increase. So for the inductance, L will decrease and C will increase. So if you have a bigger conductor, the capacitance will increase, but the inductance will decrease. Okay. If GMD increase, if you build a bigger tower to make the spacing between the two faces be longer. If GMD increase, L will increase, C will decrease. Okay. So let's do some calculation. Let's assume we have conductor which is made in all aluminum. The radius 1.3 inch, which is about 0.034 meter, about 3 centimeter. So about this big size of single conductor. And if I have two such conductors, then distance at 35 inch, which is less than a meter, so which is basically just about this three conductors separate at this distance. If it's made by aluminum, the rho will be equal to this value under ambient temperature. Okay. So resistance is easier. Resistance is just the rho times the length divided by the cross-sectional area, if you know the radius. So that will give you 0.00769 ohm per kilometer. If you calculate inductance, so we'll use the inductance formula. So that calculate 0.7 millihenry per kilometer. So if you assume you operate the system at 60 hertz, you will know omega will be omega will be 377 reading per second. So multiply by this L. So that will give you translate to the reactance, which will be 0.26 ohm per kilometer. So the inductance will generate the reactance, which is more than 30 times of resistance. Okay, so think about if you have this you make this transmission line, and if you model this line as a impedance, single impedance, so the resistance is very small. It's almost like ignorable compared to the radius of the line. So real part is very small. The impedance basically just can be treated as purely imaginary number. And how about the C? So for C, the result is 0.017 mu f per kilometer. Okay, so you can also translate that capacitance into a capacitive reactance. Capacitive reactance. This is capacitive reactance connecting the line to the ground, because we are calculating C is defined to be the capacitance between the conductor to the ground. So this value is like is equivalent reactance connecting the conductor to the ground. So M here is a million, so it's huge. So compared to the resistance, that's like 20 million times of resistance. So which means this line can be treated as inductance connected to resistance, and to the ground there's a capacitance. Okay, if you use the impedance, a circuit to model this line, so this resistance can be ignored compared to that inductance, and this capacitance can also be ignored because that reactance is too large. It's like open the circuit. So finally, the L is the most important one to model the line. So this basically matches what we're going to learn in the next session about the line model. Any question? All right, next we want to use 3 examples to demonstrate how to calculate the GMR. Okay, assume each group have either 2 bundle, 3 bundle, 4 bundle. So 2 bundle can be, the first state can be 220 kV, and second could be a 345 kV, and the 4 bundle can be about 500 kV. So if we assume each conductor is all the conductors have the same shape, and they have a symmetric layout, how are we going to calculate the GMR for both inductance and the capacitance? So first one is easier. First one, because the radius defined to be, if we use any conductor as reference, so there are 2 distances we need to consider. So those 2 will be here. We just calculate the product of the radius of first one and the distance to the second one. And because the 2 conductors are identical, so when we change to the reference, we will generate another one. So basically, which is like, for the second one, you also have ds times d, and this is 4, right? But you can just ignore, you simplify to be just square root of the product ds and d. Third one, if we use any conductor as reference, so this is the first radius, this is second, and this third one. Okay, so that's ds multiplied by d squared. The third case is a little bit more tricky. If you start from the first conductor, you have 1 R, and you have 1 D, and this is D, and this diagonal direction will be D multiplied by root of 2. Then when you move the reference from the first one to the next one, you generate the same product. You have a 4 such one group as a product, and then you calculate root of the root of 4 by 4 is 16. But basically, you just need to calculate this one. You only just, because the symmetry, you only just need to consider product of each group. Okay, because ds is 0.779 times R. If you plug in that value, so that give you so you can plug in this value, that finally will translate the number, a factor of D. Okay, so next, if we want to calculate, those are GMRL. If you want to calculate GMRC, it's same formula. We just need to replace ds by r. So that's GMRC. Okay, so they have same formula, but each place you see ds, that will be replaced by r. So on the textbook, there's one example to calculate the GMR for this transmission line. So if it's those are not bundled because they connect closely to each other. So each circle indicates the cross-sectional area of one strand. So this is like a stranding of the line. And how do we calculate the GMR for this case? So we start from any conductor. So inside there's one conductor, number 7. Outside from 1 to 6, there's 6 conductors. The outside 6 conductors, they have a completely symmetric about each other. So we can start from any one as a reference. So if it's from number 1, the first distance we need to consider is r, right? There's 1r. Then we need to draw a line to all the other conductors. So there will be also including number 7. So there are 7 items. The first one is the radius to itself. The next 6 will be the distance to the center of the other 6 conductor. Okay, so that's only using the first conductor reference. Then you can move to number 2, number 3, and 6. So you have a product of 7 elements. Okay, so that as one group. When you move from 1 all the way to 6, you generate 6 identical such group. That's 6 by 7. But you cannot use the same group for center because center has different position. So for center one, you have to, when you move to the reference to the 7, so you move the center here. So that one have the distance to the other 6 at the same. The distance is just the diameter of each conductor or the double radius. Okay, so finally you have 49 such a distance you need to count. So the last item is using the number 7 as the reference to calculate. So that's the radius of itself and the distance to the other 6. And the first item in the bracket is that basically just changing the reference from 1 to 6. And you have a totally 49 such a element, some factors in the product. And simplify this one, that's about 2.17 times the radius. If you calculate the GMRC, you take the same formula, you only just need to replace the ds by r. So that gives you this one. This one is slightly bigger than GMRL. All right. Okay, so let's move to the 3-phase double circuit line. So for 3-phase double circuit line, let's just assume there's a maybe there's a tower. And the tower just carry the 2 transmission line. Just why the 2 3-phase line? Because each one will be a backup of the other one. And here we assume those 2 are not completely separated. They actually, so for the first transmission line, they had phase A, B, and C. So this is A, B, and C. And for the second transmission line, A is here. And this is B, that is C, because of the transposition of the line. So this one means we need to define, in order to calculate the capacitance and the inductance. So we need to figure out how to calculate the GMD and GMR, right? The most important thing is to find which conductor and which conductor belong to the same group. So if belong to the same group, we calculate GMR. If belong to different group, we calculate GMD. Okay, so for phase A, it has the top conductor on the left and the bottom conductor on the right. And this is phase B, and that is phase C. And we use the same idea to calculate geometric mean values. So for the GMD between the three groups, so if we calculate GMD AB, that's the distance between group A and group B. So this is group A, that's group B. So basically, we want to calculate the distance between those two groups. We just want to find all possibility of the distances connecting one conductor in group A and another conductor in group B. Okay, so how many possible distances? So definitely this is one distance we need to include in the formula. So that's the distance between A1 and B1. So that's exactly the first item. Then we also definitely need to consider that distance. So that's A2 between A2 and B2. That's the last item. We also need to consider distance between those two. Don't ignore. Doesn't allow me to draw. Okay, that's right. Okay. This also the distance connecting A1 and B2. Okay, so that's the second element, also the distance between B1 and A2. So that's third element. So we only just have 4 distances to consider to calculate GMD between group A and group B. Similarly, you can calculate GMD BC, GMD AC, and the final GMD will basically just we do another level of geometric mean value calculation. We multiply, we calculate the product of those 3 GMD, and then we calculate their average. So that gives you the final GMD. How about the GMR? Let's first calculate GMR L for the group, for each group. So for each group, we only just study, like for group A, only just group A, right? Only just 2 conductor. So you just need to calculate the distance between the center and the skin of the one conductor, and then you consider the distance between the 2 conductor in each group. So there's the product of that 2 element. Then you change reference to the second one, you get another one. So eventually, that will be the GMR A, LA. So when you move to a B and C, they will take a similar formula. So similarly, finally, you will calculate the average of the GMR for group A, group B, group C. That will give you final GMRL. So that's the one you need here. GMRC, basically same formula, you just replace the ds wherever you see ds by the actual radius of the conductor. So now you know how to calculate the 3-phase line. So on textbook, there's one example. You consider the 3-phase line. Each line has 2 bundles, and the bundle has distance of 18 inches, and each phase has distance of 35 feet. And the total, the largest distance between the A and the C will be 70 feet. They give you the GMR for each conductor. Okay, they want to figure out the L and the C. So the radius of each conductor, the actual radius will be the diameter divided by 2 is 0.48 inch. So GMD, you just need to consider this distance, that distance, and this distance, right? So the average will be 44.094 feet. And GMRL basically just you consider each group, it will be the radius on its own and the distance between the 2 conductors of each bundle. So that will be this one. So this 12 just translate the unit from inch to feet. So finally you have the GMR will be 0.2, around 0.2 feet. Similarly, GMC, you just replace DIs by R, so that gives you a slightly bigger value. Then L and C can be calculated. All right. I will leave this last slide talking about how the capacitance can change with surface of ground to next Monday. Then we'll move to the modeling of transmission line.